Okay, for topic 6, we're going to talk about periodic functions. So, as just kind of a quick definition, a function is said to be periodic if it repeats values at regular intervals known as periods. And it just so happens all 6 trigonometric functions are periodic. Okay, and you can kind of see that if you look at a unit circle. So, do I have my unit circle? I do. So, this unit circle has a lot of drawing on it. So, let me see if I can fix that first. Okay, so if we were to look at this, let's just look at I don't know, the cosine and sine. That'll be the easiest to see. So if we were to draw an angle that put us right here, we have values for sine and cosine. Cosine is root 3 over 2, sine is 1/2. Well, what if I went all the way around and landed right back here? Well, that's a new angle. It's a new value for theta, but it's the same exact ratio. What if I went around again and landed right there? Same ratio. What if I went backwards? Same ratio. Okay. So we know that we can go around and around and around. We can do revolution after revolution after revolution, and we can end back at this point infinitely many times. So that tells me this value for sine and cosine, it's going to repeat at regular intervals, at intervals of 2 pi, for example. Okay. So we know that, for example, sine and cosine are certainly going to fit the bill. They're periodic. Okay. All right, so formally we can say, so we're like right here now. Whoops, we're right here. So we can say formally a function f is periodic if there exists a value for p greater than 0 such that if theta is in the domain of f, then theta plus p is also in the domain of f, and f of theta plus p equals f of theta. Wow. Okay. So basically what this is saying is there's some value for p that if we were to take our theta and add p, we would end up at exactly the same place. Okay. We could add 2p and we'd end up at the same place. We could add 3p and we would end up at the same place. So basically, there's some angle that if I add a very regular interval, a value for p, I'm going to end up at the same place. I'm going to get the same ratio because remember, f of theta spits out ratios. So f of theta is equal to f of theta plus p. It's equal to f of theta plus 2p. It's equal to f of theta plus 3p. Okay, so this is just a really formal way to talk about the period of a function. Okay, all trigonometric functions are periodic. They all repeat at regular intervals. Okay, now the fundamental period of a function is the smallest value of p for which f of theta plus p is going to equal f of theta. So it's the smallest interval that you're going to see that repeat happening. Okay. So we use this concept of coterminal angles and periodic functions to complete the following equation. Well, we know that coterminal angles are angles that have the same terminal side, okay? So if I have some little drawing over here, okay, and I have an angle like such, okay, and then I have another angle like such, those two angles are coterminal. They have the same terminal side, okay? And that's kind of what happens with this idea of a period. You're going to end up with the same terminal side at a certain interval. You're going to keep ending up at that same spot, okay? So if we were to look at cosine of 405 degrees, we can see right off the bat that cosine is greater than 1 full revolution. We know 1 full revolution in degrees is 360 degrees. So if I were to say, okay, this value for cosine of 405 degrees, well, it's going to be equal to cosine of 405 degrees minus a full revolution, because a full revolution is going to take me right back. Okay. So if I start at 405 degrees and I go in the counterclockwise direction, 360 degrees, I'm going to end up like right back at the same spot. Okay. So we have that cosine of 405 degrees is equal to cosine of 405 degrees minus a full revolution, which is really just cosine of 45 degrees. So cosine of 405 degrees equals cosine of 45 degrees, okay? So if I were to draw this situation right here, okay, we kind of did draw it there almost. So we have this, okay? We draw our first angle, which we know is 45 degrees, which is halfway between 0 and 90, okay? So that's our first angle. So red is 45 degrees. And then let's do blue to represent 405 degrees. So we have an initial side on the positive x-axis, and we go 360 degrees, and then we go, doggone it, it did it again. So we go 360 degrees, and then if we go 45, we end up right. Dang it. It makes me absolutely crazy when it does that. We end up right back here. Okay, so 45 degrees and 405 degrees are coterminal. They end up at the same spot. And you can see from 45 degrees, if we go a full revolution of 360 degrees, we end up right back at 405 degrees. So if you start at 45 and you go around 360, you end up at 405. Okay, so let's fill in the table. We're going to talk about the period of each of these functions in degrees and radians. Okay, so I'm here to tell you, we're not going to like investigate each of these. I'm just going to tell you, sine, cosine are both 2 pi. So we know that 2 pi is equal to 360 degrees. Tangent is an oddball. It has repetition at pi radians or 180 degrees. So every pi radians, you're going to get the repetition of those tangent ratios, okay? So half a revolution. Cosecant and secant are going to match sine and cosine, so they both have a period of 2 pi or 360 degrees. And then cotangent is going to match tangent. It has a period of pi or 180 degrees. Okay, so you do need to remember those. Okay, the good news is sine, cosine, secant, cosecant, they're all 2 pi. Tangent and cotangent are just pi. Okay, now let's use this to figure out exact values of a couple of trig functions. So example A says find the exact value of each of the following. Well, we have sine of 390 degrees. We know that's more than one full revolution. So what we can do is we can kind of peel off or subtract off one full revolution. So we could say, okay, this is equal to sine of 390 minus a full revolution, which is 360. Well, 390 minus 360 is 30. So this is equal to sine of 30 degrees. And we know that sine of 30 degrees is one of those values on our unit circle. Okay. So as we start practicing the unit circle, work on kind of memorizing quadrant 1 in particular, and you'll get really good at this. Okay. So if we were to pull up our unit circle, hopefully you kind of already know what sine of 30 degrees is, but if not, I'm here to show you. Let me erase all these lines so they don't confuse us. Okay, so if we want to find the measure of sine of 30, we have our initial side here. Our terminal side is at 30 degrees. And we know that sine is the y coordinate of a 30-degree angle. Okay, so we know this 30-degree angle intersects our unit circle right here, and sine is going to be that y coordinate. So we would say sine of 30 is 1/2. Okay, so sine of 30 equals 1/2. Now, if from sine of 30 I went around a full revolution again, that would put me at 390 degrees, which would still have a ratio of 1/2. Okay, now tangent of 19 pi over 4. We have to be a bit more careful here. Okay, so we're dealing with radians. Radians are always a little bit harder. So we need to know that the period of tangent is pi radians. Well, what's going to help us is if we can write pi radians with a denominator of 4, because then it's going to be easier to kind of see how many times we can get a period out of this, okay? So if I were to write pi over 1 as something over 4, okay, I would need to multiply the top and bottom here by 4. So that just tells me I have 4 pi over 4. 4 pi over 4 is exactly equal to pi, but we have the same denominator as our argument here, which helps us. So we have to kind of ask ourselves, okay, how many full 4 pi over 4s can I get out of 19 pi over 4? So we have tangent of 19 pi over 4. And I know that if I take this right here and I do it 4 times, so I multiply this right here by 4, I get 16 pi over 4. So I know I can take 4 full periods away from 19 pi over 4, where one period is pi, but we're writing it as 4 pi over 4. So I'm going to subtract 16 pi over 4. That tells me that tangent of 19 pi over 4 is exactly equal to tangent of 3 pi over 4. Okay, and once we get better at understanding our unit circle and practicing how our unit circle works, this will not be quite as hard. For now, I know the unit circle is brand new, so we can kind of review it and use it as needed. Whoops. So let's go to our unit circle. Okay. Well, 3 pi over 4 would be like drawing an angle like this, and it would go right here. Okay. And we're looking for tangent. And remember, tangent is sine over cosine. Let me actually do that in black because that's making my eyeballs wiggle. Okay. Well, we have that sine is root 2 over 2 and cosine is negative root 2 over 2. So that just equals -1. Okay. So we could go here and say, well, we know that tangent of 19 pi over 4 is really the same thing as tangent of 3 pi over 4. We've just kind of peeled off 4 periods, okay? And we know that tangent of 3 pi over 4 is -1. So that's how using the period can be really, really helpful to us, okay? So understand that sine and cosine, secant and cosecant have a period of 2 pi, tangent and cotangent have a period of just pi.